I became interested in photonics when I actually started in grad school. And I started talking to professors at different universities. And one of the professors said, "Do you want to grow crystals?" And I was like, I have no idea what that means. And that kind of launched me into this whole world of semiconductor growth and specifically optoelectronic devices. So semiconductors that emit, detect, or some way manipulate light. The big system behind us is molecular beam epitaxy. So that's an ultra vacuum system to synthesize or really spray paint semiconductors atomic layer by atomic layer. And what you do with that is you create devices like this. So you take a full wafer, which is just a normal semiconductor substrate like this, and you put it in a machine like that. You then take it to a clean room or fabricate it into small little devices, and then you get complete semiconductor chips like this, which is actually an infrared detector, and it has beyond state-of-the-art performance. Like, I think that's the cool part of it. We can take rocks and we can engineer them to emit light or detect light in some way. So there's a lot of different ways that quantum photonics pops up. To me, what quantum means is things that are super duper duper small. What we can do in that super duper small world is unlock faster computing, unlock a lot of different advanced technologies that we didn't previously have access to. Probably the most recent one is we leverage the quantum, not me personally, but us as researchers, leverage the quantum photonic nature of light to detect gravitational waves. And we were only able to do that by squeezing the light, or the researchers were able to only do that by appreciating and harnessing the quantum nature of light to enhance the sensitivity for detecting gravitational waves. So it turns out that when we think about light a lot, we think about it as a particle. So like when you point a laser beam, it goes from point A to point B in sort of a ray, right? And that's called kind of the ray picture of optics. In reality, all these things are waves. And that gives all these both photons, which are what light is created of, a different kind of nature. It turns out everything is really waves. Every piece of matter, even you right now, you're jiggling at a very specific frequency. It just turns out it's very, very, very low that we can't really detect it. So the kind of research that we're really interested in here is how can we use nanotechnologies to solve quantum photonic problems, or just broadly problems in optics and photonics. So not only when, the size of the thing is really small, or leveraging some of this quantum advantage for enhanced detection or enhanced computing, but also just there are needs in lasers that emit in the UV to kill COVID, for example, which is a medical problem, or making advanced photodetectors. So really, from the quantum perspective, we can use nanotechnology to create better detectors and detectors that we need for quantum photonics and quantum applications. Purely just for passive disease detection, you can use the infrared or infrared wavelengths, both emitters and detectors, to detect if someone has some specific disease. And that's because the infrared is a chemical fingerprint region. So every chemical has a very unique absorption spectra, essentially, in the infrared. And when you exhale certain particles or certain molecules, you'd be able to detect that passively with a laser detector system right in front of your breath. So it's a way that you can monitor patients without actually having, inject them or anything, actually get in there. So we have extremely a wide array of benefits with our research. And that's because of how interdisciplinary it is, right? We're optics and photonics.